All right, so here's an example of this, related to this idea where we've got some function and we're looking at the area under the curve, but we're varying the one input. And as that one bound on our integral varies, we could say, well, we have a function where that function gives you back whatever the area under the curve is between those two bounds. So for this function, like plug in g of 6, you'd be finding the area between 4 and 36 for this function. Plug in g of 10, you're finding the area between 4 and 100. It's conceivable that the area would change between 4 and 36 and 4 and 100, so g would change between inputting 6 and inputting 10. And so talking about the change of g would become a significant thing to study. And now, you want to apply the tactic that we employed above, but the issue is that x squared is not of the form of what we deduced. It happens to involve, we wanted just a letter there instead of x squared. And the issue is, man, if that was just a letter, just a single lone letter, we could proceed through the problem without an issue. But it's not just a single lone letter. So what are we going to do? We're going to set u equal to x squared. If we set u equal to x squared, then g of x can be written as integral from 4 to u of 1 plus t squared plus t to the 4th dt. But now we need to take the derivative of this. And you know what the derivative looks like whenever you take the derivative with respect to the chain rule. The derivative comes out as f prime of u times u prime. So when we take the derivative here to get to g prime of x, g prime of x is going to have to take the form of f prime of u, u prime. Well, the derivative of this integral is going to be the original function, but it's not going to be the original function just in terms of t or in terms of x. It's going to be the original function with u plugged in, because f prime u means we need the derivative of this integral with u plugged in. Now we know the derivative of the integral is the original function, fine, but now we need to plug in the u. So that's 1 plus u squared, u is x squared. 1 plus x squared squared plus x squared to the 4th. But that, yes, are f prime u something, but now we also have to tack on a u prime. And what is u prime? U prime is the derivative of u, that's just 2x. And long story short, when we simplify this out, we get square root 1 plus x to the 4th plus x to the 8th times 2x. It's a little bit tricky to go through integrals like this, but it's ultimately not too horrible. Let me just show what could happen. What if I alter that x squared some? What if I make that x squared like a sine x? What effect would that have? Well, I wish the sine x wasn't there. I wish it was just a letter. Well, replace sine x with u, and if you did, you'd get to this stage. And now when we take the derivative of a function with u plugged in, then we know the derivative is just going to be, well, I guess in this case, technically, it's going to be g prime of u times u prime. Okay, well, if the derivative is g prime of u, u prime, we need g prime with u plugged in. Well, in this case, u is not going to be x squared, is it? Now, we know that g prime is the derivative of an integral, and the derivative of an integral gives you back the original function. But in this case, g prime of u, original function with u plugged in, that's going to be sine squared plus sine to the 4th. Now, you multiply by u prime in this case is not going to be 2x like it was. U prime is going to be the derivative of u, which is going to be cosine x. And the long story short is, even if you had a function that might be a little bit more eccentric in some sense, like the sine function up there, you can play the same game. Replace it with a letter, but now when you take the derivative, you just have to apply the chain rule, which is to remember that the derivative of g is going to be g prime of u times u prime. G prime is the derivative of an integral, which is the function that's inside, but we have to plug u in to that, so g prime of u is the function that's on the inside with u plugged in. U prime is the derivative of what u was, and the derivative of what u was in this case is exactly cosine. But yeah, that idea could be applied to any such situation, and then, well, we could show off not only that we know that the derivative of the integral is what's inside, but then we also know that whenever you're taking derivatives with the chain rule, you have to start with g prime of u and then tack on u prime. And hey, that's actually a lot of knowledge shown off there in one problem. Again, we'll do more examples like this whenever we get to class on Friday.